Have you ever watched a blue flame dancing on your kitchen stove and wondered what's happening at the molecular level? When you burn cooking gas to prepare a meal, you're witnessing an energy transformation in action, chemical bonds breaking and forming, heat released, and enthalpy changing. In this video, we'll explore the fascinating world of enthalpies in different types of reactions. Whether you're completely new to the concept or brushing up your knowledge, by the end, you'll understand not just the theory but also how to calculate and apply these ideas in real life. Let's start with standard enthalpy of combustion, denoted as delta sub CH naught. Picture this: 1 mole of methane gas, symbolized as CH, combusts completely in oxygen. What do you get? Carbon dioxide, water, and a generous release of energy, about minus 890.3 kilojoules per mole. That negative sign tells us heat flows out, combustion reactions are exothermic. Keep in mind, this is measured under standard conditions, 1 bar pressure and a reference temperature, usually 298 Kelvin. Here's a quick formula recap. Delta CH naught equals the enthalpy of the products minus the enthalpy of the reactants. Simple in principle, powerful in application. Next, let's look at enthalpy of atomization, or delta sub AH naught. Imagine you have hydrogen gas, 2 hydrogen atoms tightly bonded. When you supply energy, those atoms separate into individual gaseous atoms. This process absorbs 435 kilojoules per mole. That's the enthalpy of atomization. So, whenever you see hydrogen molecules splitting, think of this number. It's the energy cost to break their bond and scatter the atoms. Let's make it even more interesting with bond enthalpy. Bond enthalpy tells us how much energy it takes to break 1 mole of a specific bond in a gaseous molecule. Consider methane, CH. Breaking all 4 carbon-hydrogen bonds requires a total of 1665 kilojoules per mole. But what about just 1 bond? Divide by 4. You get 416 kilojoules per mole, which is the mean bond enthalpy of the CH bond. This concept is vital in fields like materials science and fuel technology. Anytime you predict whether a reaction absorbs or releases heat, bond enthalpies help you estimate the energy change. Now, let's explore lattice enthalpy, one of the reasons salts like sodium chloride are so stable. Imagine a crystal lattice with sodium and chloride ions locked in a neat, repeating pattern. To separate them into gaseous ions, you must supply energy plus 788 kilojoules per mole to be precise. Here's the equation spelled out. NaCl solid transforms into Na plus gas and Cl minus gas. Delta lattice H equals plus 788 kilojoules per mole. It's like unzipping a super strong molecular zipper, energy in, bonds out. Next up, enthalpy of solution and enthalpy of dilution. Think about dissolving hydrogen chloride gas into water. As the gas mixes with the liquid, it releases heat. In a highly dilute solution, the enthalpy change is about minus 74.85 kilojoules per mole. But if you keep adding more water, each additional dilution releases or absorbs a bit more heat. This is the enthalpy of dilution. This concept matters in labs and industries. Knowing exactly how much heat will be released or absorbed keeps reactions safe and predictable. Let's apply these ideas with a quick problem. Question: what's the enthalpy change when you combust 2 moles of methane under standard conditions? Step 1. Recall the standard enthalpy of combustion, minus 890.3 kilojoules per mole. Step 2. Multiply by the number of moles. 2 times minus 890.3 equals minus 1780.6 kilojoules. Answer: burning 2 moles of methane releases 1780.6 kilojoules of heat. See, step by step, enthalpy becomes manageable. Before we wrap up, let's recap. Today, you've learned about 6 kinds of enthalpy. Combustion enthalpy, the heat from burning fuels. Atomization enthalpy, splitting molecules into atoms. Bond enthalpy, the energy of breaking chemical bonds. Lattice enthalpy, pulling apart ionic solids. Solution and dilution enthalpies, the energy changes when substances dissolve. These concepts aren't just theory. They're tools you can use to calculate, predict, and understand real chemical processes. Stay curious, keep exploring, and remember, every reaction has an energy story.